here last week. Welcome to the last week, and also welcome to the new people that arrived today. So you know this is embedded in the program for singularity theory, and we are having two different cultures meet, those from symplectic geometry and mirror symmetry, also complex geometry, but singularity theory, and we have different backgrounds and different languages. So please, when you give talk, be aware of that. A decent part of the audience might not know your common language that you speak when you give presentations, so be more careful in the way you express things, that don't use as much jargon maybe, or just be aware that it's not like a conference for exactly your topic, but it's a mixed group of different camps that all like to learn about the material. That's also why we arranged it in the way that we have a lecture series. So just maybe to give a bit of emphasis on some talks that should be more accessible, and then hopefully give the basis for the further talks that might be a bit more expertly. So we organize these series by speakers that are well known in the substance, in the matter. And typically the first talk of each person is more accessible, and then the second one leads a bit more into their research. But hopefully everything is accessible. I think all the speakers will make a great effort so that we really get into the action, because it's also supposed to be a workshop. We have time for discussions, so that hopefully there will be lots of interactions between people among us, and also new people meet each other. That's the idea. So another thing I need to announce is that we have had a little time shift. So because we weren't exactly aware of the surroundings when we planned the timetable, we've made adapted to the situation where we don't have such a large lunch break anymore. So the afternoon sessions already start at 1 p.m. rather than 2 p.m. as before. Okay. And also we have the breaks a little shorter between talks, so that you can spend more time outside in coffee shops, or if you want to discuss, right? So, so we start now at 9, or a little bit after parts of that, but they have 15-minute breaks between the talks, and then a short lunch break at the afternoon, if they have more time in the afternoon to discuss. Okay, so it's updated on the webpage. And let me introduce the first speaker, my former advisor, Bernd Siebert, from toric generation to intrinsic mirror symmetry.
Okay, thank you. Thank you, Harry, for the invitation and the opportunity to present that story here. So many of you know, and some may not, that I've been working on this program for, well, embarrassingly almost 25 years now. So I've almost a good portion of my career, together with Mark Gross. And of course a number of other people. So GS always stands for two initials. The plan is to first tell you the story that is in the period, I would say, 00 to 14, the original program, which gives a kind of generalization of toric geometry, and then announced in 2015, a shift of the perspective to what we call intrinsic mirror symmetry, that gives mirror partners to in the generality that we always hope for exists in algebraic geometry. Okay, so for me personally, that's the end of the line of constructing mirror partners. Okay, but who knows what's coming, and symplectic geometries and so on might still want to push it a little further. And then, hopefully I'll have time to explain a little bit how one, I mean, that's all about like construction of mirror partners, or even just construction of certain families of toric degenerations, of degenerating families of Calabi-Yau geometries, okay, even if you're not interested in mirror geometry, mirror symmetry. But then in the last part, I would like to explain how one might be able to prove homological mirror symmetry within this context. Okay, so let me start this with this original program. So maybe I can first say you should think of this as generalizes toric geometry to Calabi-Yau geometries. I mean, there are certainly Calabi-Yau geometries that you can build torically, but they are non-compact. Okay, so I'm talking about, they will also be part of the program, but I'm talking about things that, like the quintic, Calabi-Yau complete intersections, and a lot more. And a crucial feature of this that got us going is that this perspective provides a perfect symmetry, perfect mirror duality. It's something, if you're in the know, you don't quite expect in mirror symmetry for various reasons, but in this framework, there's a perfect duality. Okay, so it's both data on both sides are exactly the same. So let's start with the baby case that hopefully everybody knows. Oh, and on the subject of not everybody being familiar with language, if you have any questions, even if you think, oh, everybody in the room knows this, please speak up, okay? So this is a kind of service talk, right? I'm not I want to explain to people who are not from the subject necessarily how this goes. Okay, so the baby case is a purely toric thing, and it's a simple observation that if you have a polytope, let's restrict to integral polytopes, you can form a fan. Wrong pictures. Can form a fan. We're taking the normal fan, and that doesn't give that thing only up to scales. But if you also have a piecewise linear function, strictly convex, then this is a 1-1 correspondence, and this direction goes by mapping the phi to the Newton polygon or Newton polyhedron. Okay, so that's a perfect 1-1 duality, and in this context, of course, then you can obtain a toric variety. For the momentum polytope, you get a polarized toric variety, and here you get a fan. And this, if you write this down and interpret this as a mirror geometry, what this perspective would give, it's this kind of equation. I might not always write this. We'll see. Let me write this as in A4. Try to work algebraic-geometric. Okay, so and then Mumford already observed that one can generalize this by starting with polyhedral decompositions. So let me write, actually this is not what I wanted. I wanted to take this. Not something quite as symmetric. So this is a polyhedral decomposition. And I want that this polyhedral decomposition comes with a function phi. So this would be, let me call this maybe psi, and there would be a PL function which with kings, that is, I mean, piecewise affine on each maximal cell, but has kings along the codimension 1 faces. So that's a convex PL function. And then you can pretty much play the same game and obtain something that looks a little strange at first sight, maybe, but you get a polyhedral decomposition in this case of R2. Okay, so this is with the polyhedral decomposition of psi, and then if you start with a bounded polyhedron, you always get a polyhedral decomposition. Maybe I'll write here phi check, then you have a phi check here from, this would now be an R2 to R, which is also a PL function. So how would this duality work? It's exactly the same as this one. If you think of the upper convex hull of this function phi, okay? So phi gives you a graph, and let's just draw this in dimension 2, right? Something like this. And then you play the same game as up here to obtain this kind of picture. So what is this? Let's look at this. What this means geometrically. So if you it's purely toric geometry, okay? So this thing comes. If you think of this upper convex hull, it comes with a distinguished monomial, which is this kind of integral tangent vector. And that integral tangent vector here, the 0, 1, corresponds to the deformation parameter t in A1. So this thing here gives a certain degeneration that we write it as x to A1, given by t. And the center fiber can be read off from this picture. Each maximal cell gives you one component of the central fiber. Actually, I forgot to mention, when I say convex PL function, I always mean integral. So it should have integral slopes. Otherwise, you might get some non-reduced fibers and so on. Okay, so what this gives is a P1 cross P1, of course. That's the momentum polytope of P2, and this also of P2. So the X0 would really be the union of two copies of P2 and one copy of P1 cross P1 glued together in the way this is sketched. What is this here? Well, it's a little harder to explain, right? So if you look at this from the affine geometry perspective, this is really just an A2. It looks exactly as this kind of quadrant. This here is a P1 cross A2. This is also P1 cross A2, or maybe I should write A2 cross P1. A1, sorry. A1 cross P1. It's the surface. And this one is actually a P1 cross A1 blown up in one point. Okay, so you can play around with these pictures, and nice. And Mumford used these to write down degenerations of Wheeler varieties. A beautiful story, slightly involved. So, but this is like 1970 or something.
What happened when you said you might have a non-integral slope? What's like completely non-integral, like irrational slope?
No, irrational doesn't work. Rational slope. No, irrational doesn't work. I mean, that would be in the realm of rigid analytic geometry.
But you can make sense of it in some. If the slope irrational, you can still make sense of the mirror.
Yeah, but sure. I mean, you know, right? I mean, what will happen is that these lengths are not rational anymore, integral. They become real. So it's like a kind of real polarization or something. Now this side is much.
Yes, you can, but the categories become infinite. You have infinite exceptional collections.
Yeah. Okay, so then what was the thing that or program that we initiated? So with this, in this way, you're always talking about rational variety. It's a little boring from the perspective of mirror symmetry or of algebraic geometry. They have all of these have algebraic chloride inside. So, but you can introduce, you can turn this into something, let's say, curved or a sphere or something closed, if you admit singularities of the affine structure. So you drop the assumption that the whole geometry is embedded in Rn, and just ask this picture to exist locally. So we start with a manifold. So we replace this psi by an integral affine manifold. I mean, real manifold, right? Affine has several meanings in this subject, I'm sorry. So it's not the algebraic geometry affine, it's the affine from affine like geometry in an affine space. R manifold that we call B. with singularities. So rather than giving you a formal definition of what these singularities give, let me just draw some example. So I'm not drawing some kind of sphere or something, or we'll do that very soon, but let's still look at something that will essentially still give a degeneration of P2, but which is in a slightly more interesting fashion. So these crosses here, so this is really, I mean, the maximal cells I'm drawing are exactly as they are drawn, okay? So these are the integral, this is the integral picture. The picture is also correct in terms of affine geometry at this point, okay? So I'm drawing a chart near these points. So an affine chart. So, but then I'm thinking of cutting, doing some kind of, so the affine structure is not correct on these dotted pieces. What you have to do here, if you draw a chart, you can actually make this kink here straight. Actually, I took a bad. I made a bad choice here. Let me try to do this a bit more complicated. Let's do this one. It's easier to draw. So I'm not doing anything to that side, but then the other one comes over, and so this would actually be like a 2-1 minus 2-1 direction, okay? And this is 1-0, and this is minus 1-0. Okay, so that would be the correct fashion. So so what's happening at these points? At these singular points of the affine structure, of course, you can do parallel transport, right? So you could start somewhere and go around and see what's happening with your affine structure, and you get a monodromy. Okay, and the monodromy in dimension 2 that I want to focus on always looks very simple. It's like this. Okay. So another way to draw this chart is you could also say, you take out something like this, right? And then what I've drawn is this transformation, hopefully. Okay. Okay, so then I'm already ready to if you have swallowed this kind of language, maybe I should stop here. So is anybody lost already?
I have a stupid question. This red monodromy, is this something that I should see from the picture, or is it the additional
With some experience, you can see it. Otherwise, no. Okay.
So
you shouldn't feel bad if you can't see it.
No, but
right. It's especially here because it's tilted. It's hard to see. What I'm saying, the monodromy is, sorry, this is also not quite correct. It's conjugate to this one. Okay.
But this is something that you can code in the picture. It's not an additional data that you impose.
No, it is not. Sorry, not in this picture. I would have to tell you that these are conjugate to this one, and then everything is fixed.
Okay.
Yeah, good question. Thanks. Okay, so right. So, but then you also have these piecewise linear functions that I'm kind of speaking and incorporate. That's a choice, okay, and everything I'm saying will depend on it. So the main theorem in this framework is the following. That took like 7 years of work or 6. You start with this data BP phi. So P is a polyhedral composition that you see in the example. Of course, also over the integers. So these are integral polytopes. So this has a bunch of cells that are phase fitting. The whole thing is a manifold. And then you have this PL function, or maybe it's multi-valued also. I mean, because you can imagine, right, if you do this more globally, the thing won't fit. But it's some kind of multi-valued thing. But locally, you always have this kind of picture. So there's a 1-1 correspondence.
Phi stands for the monodromy.
See, excuse me?
What is phi?
Phi is a PL function, like here. Yep, that was it. Yeah. So in general, multi-valued, meaning it's only defined up to affine functions. So the only thing that's really matters is kind of the change of slope at the encoder metric watch. Okay, so and then there are these families X to spec. So I'll give more refined versions soon. Which contain X0, which is the generalization of what I do on this thing here. So it's a union. You take all the maximal cells, and for each maximal cell, you have a toric variety P sigma with momentum polytope sigma. Okay. So it also comes with a polarization that restricts to the given polarization on P sigma that you get from the momentum polytope picture. Okay. Right. So not quite. I wanted to say something slightly more interesting. So there is also a factor of C star to R, where R is the number of log moduli. And I'll try to explain this later on. So without this factor, everything looks completely discrete, right? And you might wonder, where did the moduli go? Yeah, so I mean, these things, these central fibers, you could do something like the degeneration of the quartic to a union of three hypersurfaces. And of course, it has moduli. Has a lot of big moduli space. So where does this disappear? And it's lurking in the thing. Okay, so I'll give a list of features. I'll discuss a list of features where you will see that these are actually not just kind of very discrete things, but they produce universal families. Okay. So just for my peace of mind, so in dimension 2, I would insist that all the singularities are like this. The theorem is a little more general. You could, especially in high dimensions, it becomes pretty kind of subtle. So let me restrict to what we call simple singularities, and simple affine singularities. Then this is what I'm saying literally 2. And I'll try to give you a little bit of an idea of what this means. Okay, so then let me give you one example.
Simple affine singularities are the singularities of what?
Of B.
And the total space X, is this singular or might be singular?
It might be singular. It would have, so in dimension up to 3, the generic fiber, the generic fiber is smooth. Okay, you will see, you'll get typically some kind of type A singularities on X0. So each of these, yeah, this person could produce an A1 singularity. I'll say this in a second.
So there's a general statement like that in general dimension.
Yeah, we know the similarities for, yeah, we have toric models for these similarities.
If one is not the same as one on a middle board.
On the middle
The
board.
arrow one.
It is. No, no, it's not. This is kind of, no, this is the,
Just making sure.
yeah, this is a mirror transformation. This is not a mirror transformation. That's like the construction from a momentum polytope to a
We still
toric
have
variety.
same on a bit.
Yeah. Has a different flavor. It's true. Okay, so yeah, so I wanted to give the example of supporting. So there's already quite a beautiful story when you restrict to dimension 2 and triangle some polygon decomposition of the 2 sphere. So, for example, you can produce something, and now I'm already doing something slightly different than the one with the simple singularities. I could put singularities here that look like fourfold simple singularities. Oh, these are called focus-focus singularities. So these things are called focus-focus in the integral systems community. Remind me that I wanted to say something about the symplectic, if I forget, the symplectic history of this kind of focus-focus singularities. Okay, but let me first do this here. So if you feed this into the program, into this program, so this is really a union. So I should tell you what this is. This is integral length 4. So I need to add 3 points. This has nothing to do with the single points, but this thing has length 4, integral length 4. Okay? So this is the BP. And I'm not telling you what the phi is. You take a kind of minimal phi. And what you will see is that you could, for example, obtain the dwarf family of quartics. So this would be the family. Not quite. Has an interesting twist. So you take a product. So this sits inside P3 cross. Let me see. This may not be A1, but let me take. No, actually, it is an A1. I don't know what's the radius of convergence. I'm a little unsure here. Let me write this analytically for you, okay? So product xi, I put 0 to 4, 3, plus, and then typically the dwarf family would put a t here, but that is not quite true. Some xi to 4. Okay, so the dwarf family is when you put a t here. What we obtain is something that first looks a bit like a defect of the theory, but is a very important feature. Okay, you obtain an analytic function in T, which turns out to be a Jacobian theta function. Okay, that or a quotient of those. So there's some certain analytic expression, and that's why this family typically only lives over this kind of complete local ring. Or
It's like that it's equal to 0.
yes. Over a complete local ring, or actually, as we'll also see, it also exists as a homomorphic family. Okay. Okay.
This is by some approximation here.
No, I'll show you. Okay. Okay. So this is one possibility. Because in these situations where I don't have simple singularities, I need a little bit of more data, which is essentially a kind of Laurent polynomial of degree 4 along each of these edges in some compatible fashion. But each choice of these choices produce you one parameter family, and you can get all kinds of cool singularities here, like K3 surface families, one parameter degenerations of families of K3 surfaces where certain types of singularities fixed. So we get all kinds of one parameter families of quartic surfaces with AD singularities where D is less or equal 1, less or equal D, less or equal 3. Depending on what you choose. So, for example, what is it? I want to say something. Yeah, for example, you could have 6 A3 singularities, or 24 A1 singularities, and so on. Can play all kinds of games. And incidentally, I mean, there's an ever unfinished project, but hopefully coming along very soon with Mark and Paul Hacking on and Sean Keel, where we use these kind of.
If you write a DP vector,
Excuse me?
24 A1 singularities.
Say again?
If you write your family,
That would be the 24. Yeah, yeah. It will. Yes, that would have 24 singularities. Yeah.
and it is the O of T2 that makes the difference with the number of
No.
singularities.
No, this is totally irrelevant. I mean, yeah.
So what do you mean you can get 6 A3 singularities?
You have to. Yeah, it's actually I don't know the equations. If you ask me for
By
equations, I might
changing
have
the
a hard
equation,
time.
sum of x cycles.
Yeah, you would change that.
You change that.
Yeah,
Is
essentially.
it 3 or is it 8-4?
Sorry?
Is it 8-3 or is it
A4. But I mean, it depends on the notation. For you need 24 fibers.
that should be a 4. Yeah. Yes. Okay. So right. So I was just sending one information that was
I don't think so. So it's very hard to reform S3. You cannot inform A4 with 4 singularities in the same fiber.
it's wrong, right? Is it
Yeah.
A3? It is A3. Yeah, it depends on. I mean, for me, A3 is the one which has a 2, 4 in there, right? X, Y, Z. X, Y minus Z to 4. That's an A3 singularity, right? Okay. So with Mark, Paul Hacking, and Sean Keel, we get some toroidal geometric family toroidal compactification of moduli space of polarized K3 surfaces. With a family of singular K3s. So this is where one thing is. Okay, so then if you believe that statement, so that's a construction, right? That's just a generalization of toric geometry. You start with some discrete data, you get some geometry, some algebraic geometric thing, except now it's not a single variety, and it's not as easy to write down as you will see, but it's this kind of construction. And so how would mirror symmetry work in this? So you start with BP phi.
It should be 12.
Yeah, you get not as many as A1.
Ah, damn it. Yeah. Gosh, yeah, sure, it should be 12. No, I get 24. What am I doing? 6 times 4, it's 24.
You split this is the one you split it into 2.
No, I split
So
it
if you
into.
split the 4 into 2.
No. This thing will give 4 focus.
I know, but to get A1s, you need to keep them together.
No.
If you split them, you won't get a singularity.
Yeah.
A simple singularity will give you. Oh.
Yeah.
You get me confused. Okay. Yes. Maybe that is no. That was correct.
That's correct. That's the one.
That is correct. That keeps the 4. Yes, you're right. So it's 12. I need 2. Right. The one with the 1, 2, 0, 1 gives an A1 singularity.
Wait, but this equation that you improved, the equation in the top, it has 24 A1 singularity, the central fiber, right?
This does have 24. What am I doing? No. This is the general fiber is smooth. It has 24. That's what confused me.
Yes.
I'm talking about the families. Okay, the generic fiber has 12.
Okay.
Here's a generic fiber
But
for
there's-
smooth.
Okay, so
The total space.
That's the generic fiber. You're saying singularities of the generic fiber.
Yes.
Yeah, those are-
Yes.
and so for this you would need to change the equation to something.
Yeah, it's something more complicated. Exactly.
Okay. But somehow also it will corresponding to this picture on the left.
Yes.
So,
Yes.
so the picture encodes more equations than just this one, or
Yeah, I didn't want to get into this. So there's a whole moduli space of, in the non-simple singularity case, there's a moduli space of such things, and you can analyze what's happening.
okay.
There are these spaces of functions, and depending on how you choose your function, you get different kinds of singularities of the generic fibers. Okay, Right, so how does one get mirror symmetry here? So this corresponds to the family X over, let's call it S, and then plus an O of 1. Okay, and then there's this kind of duality that I try to sketch here, called a discrete Legendre transform, that changes polytopes with fans plus PL functions. And it is really a discrete version of the Legendre transform in Hamiltonian dynamical systems. To something that's called D-check. Oh, this doesn't work very well. Which then corresponds to some mirror thing. Mirror degeneration, okay? And that will be mirror symmetry. And in this case, it's a perfect job. Okay. So of course now you have to think about what the possibility is to vary these things and make sure that matches with the expectation of mirror symmetry. But trust me, it all works out as beautifully. Let's just continue.
So this S is the set of the formal.
Yeah, I'll tell you what we should really do, okay? Because this doesn't look right. You're right, yeah? So the complex moduli space, the complex geometry should be, complex moduli should swap with the scalar moduli. And that's what's happening. So the base set of, so maybe I should write as check. So this is really not, it's not always the same complex parameter space. Okay, so then let me see, now we have a long list of features that might end all the way to the end of the talk. Let's see. I have like, what is it, a little more than half an hour now? Oh, there's a okay, so the phi is really what gives you toric models of this map pi to the base, okay? Just as what I just erased, but only near the zero-dimensional strata of X0. So which correspond to the vertices of the polyhedral decomposition. And that's just as in the Manford degenerations, yeah? That I presented. So addressing what Umut's question or remark, there's a universal choice of phi. So this is now, it comes with a parameter space. It's given by, so it takes values in the dual of all in a certain monoid. So these are some multi-valued piecewise linear functions, strictly positive, okay? So this is a universal choice of phi, and that gives us a much bigger family. It gives us family over something spec C. So this will be my, oh, sorry, takes place in dual. I'm just right. That is Q here. So and then, oops, the completion of this is a toric ring that you can complete at the zero-dimensional stratum, and then you replace your spec CT by the spec C double bracket Q, and the other one stays unchanged. Okay. Dual. That means dual. Okay. And as monoid, so dual cone if you want. So the simple singularities exist in all dimensions. let me just draw. So in dimension 2, I gave you the complete list. Okay, it's just this focus singularity. Very simple. Oh, I wanted to make this remark. So Margaret Swimmington, around the same time when we worked on our program, suggested to use such pictures in dimension 2 to construct symplectic surfaces. Okay, so you will find very similar pictures in her work, and it fits perfectly to what we are doing in dimension 2. And the correspondence has been used more recently in work, for example, by Pierre Rousseau and Julia Auguste. Okay, so and the simple singularities, let's just draw in dimension 3. There are two types. The ones that you actually expect from the SYZ picture of mirror symmetry. So these are three. So in that dimension 3, so this is, I'm drawing an edge of your polyhedral decomposition along with 3 adjacent 2 cells, and that separates 3 cells, okay? And then there's some singular locus of the affine structure that in this case would produce monodromy around these 3 kind of wiggly lines. Why am I drawing them wiggly? In our picture, we never have a precise location of the, or we never need a precise location of the singular affine locus. Okay, all we have is, okay, we know what the affine structure is in the interior of maximal cells, and we do know what the affine structure is at vertices. And then we know there is some singular locus somewhere. Okay, so in whatever choice you choose here, whatever choice you make, it produces a singular affine answer. Okay, so this is one. And then what is Legendre dual to that? Legendre dual to that is this picture. Now, depending, there could be more flaps coming off, okay, that I'm not drawing. That's also okay. Yeah, I'm not sure how to draw this. Okay, so there could be a lot more. You take, so this projects in this direction to a 2-dimensional fan. You take the dual polygon to that, and then these 3 things correspond to 3 edges. Let's say this is this one, that one, and that one, and then you would have something like this. Okay? And this is, of course, just a 2-cell of your polyhedral decomposition, so it separates 2 3 cells. Okay, so that's a full list again of these singularities, simple singularities in dimension 3. In high dimension, it gets a lot more complicated. Okay, but it's a bit combinatorial involved, so let's skip this. Okay, so if you have simple singularities, we actually know that this pi, we have toric models not only near the vertices, but at each point. We also know the deformation theory of these. These are kind of rigid singularities in logarithmic geometry. So in dimension 2, again, it's very simple. So you would have some x and y and w, and then the singularity. So let's say the w is actually a toric coordinate, okay? Then this would look like something like a 1 plus lambda w times t. Forget what's the 1 w. Let me scale w. Okay, 1 plus wt. Of course, this is just, you see here how the A1 singularity comes in, right? So for w2 minus 1, there is an A1 singularity in the total space, but the general fiber is smooth. And we have similar models in all dimensions. I'm trying to sweep this under the carpet, but in a way it's important to make sense, really precise sense of the statements when I talk about moduli. This whole picture comes with a log structure. So the pi, and it's easy, I mean, the way we first defined the log structure on x0 and by hand. But with hindsight, it's just the log structures that you obtain by looking at this family. Okay, so you could restrict to one parameter of GMR. It's a one parameter family. The central fiber is a divisor in the total space, and whenever you have a pair of a divisor in a total space, you obtain a log structure. So pi, this provides you a log structure. So let me just write this. So let's work over CT. So and maybe take R equal 1 and then over S equals C spec C double bracket T. Okay, to make this correct. And then the log structure would actually be this Mx is the Ox minus x0 cross. It's a little sloppily written. Hopefully you don't mind. So it's irregular functions that have zeros only on the central fiber. It's a multiplicative sheaf of monads, and the log structure is the inclusion into the sheaf of regular functions. And it's called typically the alpha morphism in log geometry. So it comes with this log structure. There's this whole subject of log geometry where you enrich your structure sheaf by this such sheets of monads, and then the whole purpose of this is to enlarge your one motivation for this is to enlarge your source of smooth geometry. So anything that's toric becomes smooth in this language. So we are kind of toric, except we have these annoying A1 singularities, and that's pretty bad from the point of view of log geometry. But we managed to get this going. I mean, it's something that Arthur Ogus calls relatively coherent, fits beautifully, and it has a deformation theory. We wrote this down and so on. Everything works as expected, and Simon and Mate, they have a generalization of this work.
What's the relation of the general fiber of your family? If it is holomorphic, it is extravertible, and the fiber at radius 0 for the Kato-Nakayama.
I'll get to that. I get to it in the Kato-Nakayama thing. You're wondering about the topology.
Yeah.
Yes, I'll tell you. Yes. That's true. Yes. Okay. So and then of course the central fiber you can restrict, right? So we also have this Mx. Oops, Mx0. You see Mx restricted as a log structure to X0. Right. So now this makes sense, or at least formally. I'm not sure if it makes sense to you, but so when I restrict this family to t equals 0, I get a family of log schemes over GMR, and this is actually universal. Okay, it's a universal kind of family of over the standard log point. So restriction, so x, x0, mx0, over GMR, that you have to change this correctly. Maybe I should remove this and just do x0 cross GMR, okay? All of this. Then everything seems correct. That's a universal family.
Universal or semi-universal?
It is actually universal if B is closed. It is actually universal family, so that's something I just had. B closed, or the boundary of B is flat in affine geometry, so totally geodesic. Then this is also true. Okay, so we also have control of the Hodge theory in the simple singularity case. In high dimensions, you have to be.
What means totally jersey? What is it?
Excuse me?
What means totally jersey?
It's just it doesn't have kinks. Yeah, you want it to be an affine manifold with singularities itself of one dimension less. So a polyhedron without singularities does not fulfill that.
So I don't understand. Is this about the smoothing, or is it just about the?
This is not about the smoothing. Okay, so there's some Lock deformation here is a little kind of unintuitive. If you
Sorry, but no,
this is
about the full.
no.
No.
This is a statement we could make before talking about smoothings. It's really just on these kind of locally trimmed deformations. But then when you have the family, it also is then universal in the sense that you might think of. Okay.
Is there a reference for this?
Yeah, it's written it up in the paper on periods.
So the point is that there are locally trivial deformations, and that they are universal is easy to show. But then you also want to go in the smoothing direction. And then that is also universal, that's harder to show.
But that's
also
it's true.
It's also true, yeah.
The local modular space has a CT algebra structure. And then you have directions for t is equal to 0 and the direction.
Yeah, I think I understand the statement. I was asking for proof. Is it written anywhere?
The proof is by doing period intervals and working hard to show that you get enough moduli and so on, and checking the local deformation theory.
So why can't Nietzsche use this, for example? Okay, anyways, I'll ask.
We can discuss later, but I'm not sure what.
Yeah, I'll say later.
Okay. So then the next thing is. So we also have control over the log Hodge groups. They are reflected in affine geometry. So you can compute that JHP. So the correct statement is you have to push forward the thing you get, which is good. X0 okay, so J is the inclusion of this bad locus where you have these singularities of the affine structure. So that's codimension 2. Log singular locus. That corresponds to the singularities of the affine structure correspond to the things that we had in A1 singularities in the total space for the quadratic, let's say. So you remove those, you push forward a locally free sheaf that always exists here from log geometry, and you compute this log Hodge groups. And that is also isomorphic to the HPQ of the generic fiber, okay? So this is maybe I should also say this is isomorphic to HPQ of a general fiber, generic fiber, so it's either. And this is equal, I'm writing equal because it's a canonical isomorphism to HP of B Yoda lower star, which P, unfortunately there's a little bit of a strange, maybe I should write this differently for this audience. Let me write this as TBZ. Does this make sense? So I mean the integral tangent vector fields. And then a tensor this with over Z with K. So that works for a ground field, so think of the complex numbers, okay? This is computable, it looks a little intimidating. Oh, the Yoda is the inclusion of the complement of the log singular locus, log affine, of the affine singular locus. Locus of affine singular locus. So you take the P vector fields, vector fields, alternating vector fields, push forward, and then compute the sheaf cohomology of that. That's computable. Okay, so if you give me, or I give you some integral alpha manifold, one can, this is linear algebra. Okay, it's very much computable. Didn't you once write a program to do that for certain examples? Yes. Yes. So it is definitely computable. Okay. So as a corollary, you obtain this Hodge theoretic mirror symmetry. Oh, and it's it's a bit of a white lie again. If this is always true if P or Q are 0, 1, n minus 1, or n. Okay. Otherwise, if n is bigger or equal 4, we need a little more. So we call this super simple. So there's certain momentum, monodromy polytopes that are always simplices, but they are elementary simplices, meaning they have the only integral points are the vertices. Starting in dimension 3, there are such things that are not standard simplices. Okay, so and here you would ask all the monodromy polytopes to be standard simplices.
So n is a fiber dimension.
N is a fiber dimension.
Some of the P's, yeah, Q's. Who is Q?
Oh, sorry. Thank you.
Is it not the other way around?
No,
Usually the other way around. Usually the other way.
this one is the other way around.
Wow.
Okay, so then the other thing, so the corollary is that we have that HPQ of this X is actually also equal to Hn minus P comma Q of X check, as expected if these are these mirror dual things. So this is Hodge theoretic mirror symmetry. That whole family also comes with a holomorphic end form, with, well, log holomorphic volume form. So the omega is trivial, so without zeros. So this means that the omega n x over s is actually, the logarithmic one is trivial. So it's a Calabi-Yau geometry. So this means it's relatively Calabi-Yau. Okay, so and then there is something rather unexpected, that if you look at the polarizing line bundle that comes with your construction as well, it has a canonical basis of sections. And they're parametrized, labeled by the 1 over d integral points of B. So B is an integral alpha manifold, so you know what integral points are, but you also know what integral points with denominator D are. Okay, so there are a bunch of these, you can count them, and that gives you the space, the dimension of the space of sections. But more than that, for each of these, they extend canonically to the family. So that you should think of analogs of monomials in toric geometry, but they are not monomial typically. Yeah. So it's quite unexpected. But if actually, so a trivial example that was already known to Mumford, so to speak, if B is a torus, a real torus, so some lattice, then so this is the X. I'm switching notation. I'm sorry. The X over S is a Mumford degeneration of abelian varieties, of polarized abelian varieties, and the theta p are actually the Riemann theta functions. So we retrieve all the Riemann theta functions from this point of view. I'm German. I should say pronounce it correctly. Riemann. Okay, Riemann theta functions. That you can use this in our theta functions. So we call these, for this reason, we call these theta p generalized theta functions. Unfortunately, many people will think of something else when we say that, but anyway, we still do. So that has the kind of really unexpected statement that any of these families, like these quartics, quintic, Calabi-Yau, whatever dimension families, they from that construction come with this canonical basis of sections. Then maybe let me say the following thing that actually is really linked to the next point, but something I did together with Helga, as already mentioned, pi extends, at least locally in the space S, right, which was a spec C double bracket Q cross GM to R, and now I should rewrite C star to R. Okay, I want to make an analytic statement. To an analytic family, to a complex analytic family. So now I want to use a curly X, and this will be a dis cross dis to R. So this, so I want to distinguish these two. Sorry, this is not a disk, damn it. Some U in this toric variety. Maybe I should write spec C, whatever, cross C, what did I write? C star to R. Disk. This disk to R is in C star to R. So this was in our paper on period integrals.
Questions about this for the quintic, for instance, right? This basis of sections. What's the dimension? Like what's the projective space you embedded?
Well, you can read it off. I don't know for the quintic off the top of my head. You just count these. I mean,
but there are a huge number of them, right?
I mean, for the quintic, you can compute what's the dimension of OP, right?
So what is it?
What do I know? Some formula. I mean, see. Actually, we were wondering about this yesterday night. I don't know. I have to.
But is it like roughly speaking, like number of the integral points in the polytope?
Yeah. The one over the integral points in the polytope. Exactly. Okay, so then comes something cool. So this R is the same R we had before, which gives the dimension of this log moduli.
So what is the meaning of this locally in this statement? What does this locally?
Well, locally analytical, right? So our family lives over C star to R.
Spec is just a point.
Excuse me?
Spec is formal.
No, we have these. Where is it? It's still this factor, right?
So it's the local is about that factor.
Both. I mean, the whole thing. This. I mean, this has some topology, right? So it's you take a point in the center fiber, and then it has this analytic neighbor. There's this family, such that if you complete, it takes a corresponding thing, you obtain that one. Okay. So beta 1 to beta R. Yeah, so beta 1 to beta R, that's again multivalued because of monodromy around the center fiber. families of two cycles, continuous families, in this total space. Sorry, not two cycles, n cycles. In this analytic family, okay? So X to, what did I say? It's this U cross. Let me go again over work. Let's work again over one parameter. So Q equal n. And this is really a disk across this to R. So the multivariate, so there's a monodromy around this factor, right? This has a T coordinate, and if you go around, there will be some topological monodromy. So and in X, with the fact that if I restrict beta I, restrict it to X0, that restricts to X0, and then there is this, I haven't mentioned that, there is a singular momentum map, or degenerate momentum map. What I mean by this is that the X0 has all these toric pieces in there, right? P sigma, and P sigma maps to sigma. And that is literally the momentum map, you know, from toric geometry. Okay? And there's a global version of that. That easiest examples is just put together these things that will fit. If you introduce parameters, you'll have to be a little more careful. But anyway, so that exists. So beta I maps to B, and it is a family of the image will be a graph in B. And the fibers are n-1 tori, real tori. So that's an n cycle, and it factors, I'll draw a picture in a second, fibered in S1 to n-1 generally, general points, over a, what we call a tropical one cycle.
But this is beta or beta minus delta?
Beta minus, no, it's, well, the image is actually B minus delta, but yeah, if you want, I mean, no,
I see.
this maps to B.
B minus delta.
This maps to B. Otherwise,
But the image
the
is
beta I lies in B minus delta. Okay, because that's what it, yeah. Yeah, so let me first, let me draw some simple example. So let's say, yeah, something like this, right? Let's go back to the example I had in the beginning. So there is a tropical cycle that looks like this. Okay, and something, of course, interesting is happening at these points. So at general points, you have an n-1 torus. So over an edge, you would have a cylinder. And then there are three S1s coming together. It's probably similar to what we'll talk about a little bit. The match, and then you have to fill something in to turn it into a two cycle. Okay, so there are these two cycles. That's what topology has to do with physical diagrams, but
there's one and minus one is not half dimension.
it is half dimension.
You said fiber dimension and
Complex dimension. Complex n dimension is real n dimension. Right?
yeah, but fiber dimension. This is real n dimension. This means fiber dimension is n minus one. Complex dimension is n
No,
minus
this
one.
n. So beta is an n cycle, real n cycle. And so, okay, so let's say for the quintic, it's real 6-dimensional, complex 3-dimensional. These are the three cycles. So, and what I proved with Helge is that we can, so these are n cycles, and you can compute an integral of the homomorphic n form that's given to you from the construction over these n cycles. And these are part of these kind of paired integrals that you are interested in mirror symmetry. This is the one that gives rise to what is called the mirror map. And what we showed is that these are kind of trivial, in the sense they are completely monomial. and you can compute them. So you take the integral over beta I omega. The tropical one cycle, I need some notation for these. Let's call them beta I trop, okay? And what this is, it's a zi, and the z1 to zr are coordinates, are the linear coordinates of c star to n, c star to r. And then there's a certain t polynomial coming in, some t factor, okay? Ci of phi, C1 of phi composed, paired with beta I trop. Let's not worry about the meaning. It is something you can compute, it's an integer. Okay, so this is just a monomial times the constant. So whenever you fix your z1 to zr, you take this one parameter family, it's canonically parameterized in the sense it's a constant times the t power. Typically, you would expect some holomorphic function in t or a meromorphic function, but it's just a t power. So this is monomial. I.e., the mirror map, if you know what that is, that you need to equate paired integrals with Gromov-Witten potentials is trivial.
It doesn't even contain the smoothing.
No, it does. It's a family over.
You found R functions.
It's a family parametrized by t.
But you found R functions, you shouldn't you find like R plus the dimension of the first?
These are these coordinates.
Yeah, he has a good point, right? We're lacking one dimension.
Why is it lacking?
That comes from an edge.
Sorry, what? Where's it?
You have R cycles, but the thing is R plus one dimension. So for coordinates.
No, this is correct. What's written? There are R plus one, z1 to
But it's
zr.
not about the form, it's
and then
about
one.
the number of coordinates.
Coordinates of what?
So should
There's.
this family is R plus one dimensional, so the mirror family should also be R plus one dimensional.
I'm not talking about the mirror family. So, okay. So you're not complaining about this thing. You're confused about this statement.
I'm confused about the numbers. Why are there R coordinates?
Forget about this here, okay? So there are R coordinates. We're good with that, right?
Yeah, so this is just on this log parameter,
Yeah,
not
but
on the smoothing.
it is.
No, T is the.
T is the smoothing parameter, okay? That gives a family. So we have R families,
So it's
R
not T,
one
you
per
should
meter.
think of it
It's
together
R
with
one
T.
per meter families of
T is
n
already nice.
Yes, yes. Okay? So now comes the Calabi-Yau phase and how we control the topology. That's of course also coming having to do with what I said here and how it relates to the classical SYZ picture of mirrors.
So omega needs to be chosen.
Excuse me?
Omega.
No, that's the one that's given. This is my omega. Well, maybe bad choice.
Omega canonical.
Yes. In the construction. I mean canonical. It comes with the construction.
So are you deforming the pair of the space and omega, or are you deforming only the underlying space?
Are you asking for deformation theory?
That's universal for space plus volume form or for space?
For space.
But then you have a choice for omega.
If you think just abstractly, yes, but not from the construction. Right? Just like a toric variety comes with a canonical holomorphic volume form, right? Or log volume form. Some xi inverse dxi. That's canonical, right?
So that's the real. That isn't that a more fundamental statement that this omega is the special flat holomorphic volume form. Once you have that, then of course there's a.
It's not flat. That's not true. It's a normalized holomorphic volume form. Yes. Yeah, that's what I'm essentially saying, right? It's normal. I mean, this is no, sorry, the normalization. No. That's a trivial part of the statement. So there's another end cycle, which is a kind of SYZ fiber. And that is on the nose. I mean, without doing anything fancy that I did with Helga, you can compute that the integral is 2 pi over to the power n. So that
is unique, right? That answers this question.
That normalizes that. Exactly. Okay, so let's go to topology. So let me look at the analytic family and restrict it to absolute value t equals epsilon. So that's a smooth family of Calabi-Yaus, and that is the same, it's homeomorphic to the Kato-Nakayama space of the central fiber. And that is a general statement that Nakayama and August proved. So where certain log structures relatively coherent, log structures relatively log smooth, they have this statement, so it applies to our setup. I'm not going to explain exactly how to get the Kato-Nakayama space. So the people that know there's a canonical way to produce a topological space from a log scheme over the complex numbers. And here our log scheme lives over one perimeter family. So this Kato-Nakayama space also can be restricted to the central fiber. That gives a family over S1. This comes naturally with a map to S1. And that is homeomorphic, fiber-wise homeomorphic to the restriction of the family to a small absolute value of t. So I'm not sure if
Checking in terms of time, we have a bit.
oh, yeah, should stop here. Yeah, it's maybe a good point to stop, actually. Okay, yes. So I'm essentially, I'm done with I'm done with the list of features. So next time I'll try to explain hint and how the construction goes, and then move on to the intrinsic mirror construction, even briefer than that. And then hopefully be able to say a little bit on homological mirrors.
Okay, let's take the time for a stop.